Hello, and welcome to the Characteristics of Polynomials video. There's a lot of information we're going to be going over today. I'm hoping most of it is review, but feel free to watch this at a faster speed because I know this will take a little while, particularly because each question has many different points or parts. First, we're going to be looking just at some equations, and then we'll spend some time with some graphs. So if we zoom in a whole bunch, we can see that for each question, we're going to be doing 5 different things, and we're going to be covering 2 of these questions and then a couple graphs. So first, we want to write an equation in factored form. Then we're going to convert the equation to standard form, which means a lot of foiling, multiplying everything out. Then we want to find the degree, determine the end behavior, or which direction would the arrows go on the graph, and find the y-intercept. So I'm going to be going through each piece of these problems, as well as doing some notes on the side. So let's get started. Oops. There we are. So if we take a look just at problem number 1, all we have is that we got -5, 2, and 1. And we're saying, given these roots, so that means that we have x is equal to -5, x is equal to 2, and x is equal to 1. That's kind of how we're starting out the roots, or you can think of them like x-intercepts. So if we want to do the first step and write this in factored form, think about doing what we did when we were factoring in our very last unit, but kind of backwards. You know, when we would solve and we would have something like x plus 2 times x minus 4 is equal to 0, you know, when we get to here and I'd say solve for x, well, we would set each factor equal to 0 and then solve from there. So here we would have x is equal to -2. Well, now we want to go backwards. We're going to add 2 to both sides and set that up in a factor. Or in this case, our factors would be, for part A, x plus 5, x minus 2, and x minus 1. And again, we're setting all of those equal to 0. So that's how you can set up your factored form. And that's the first step. First step already done. I think the next step is probably the longest, where we are converting the equation to standard form. You're going to have to use FOIL a few different times. So we're going to start by taking our factored form. So again, this is step B. Taking our factored form, and let's FOIL with just 2 of the factors for now. So just use the first 2. So we'll do x times x, x times -2, 5 times x, and 5 times -2. So this becomes x squared minus 2x plus 5x minus 10, and we still have that x minus 1 there. So once I've combined like terms, I'm going to get x squared plus 3x minus 10. Excuse me, my computer is open, you can hear my email. And that's being multiplied by x minus 1. So now we're going to do the same type of thing, and we want to make sure everything's multiplied together. So we're going to do x squared times x squared times -1, 3x times x, 3x times -1, and then -10 times x, and -10 times -1. You can do this kind of as like a rectangle box method if you'd like to multiply it out that way, or you can think of it as like an extra big FOIL. So see, we're going to have x cubed minus x squared plus 3x squared minus 3x minus 10x plus 10 is equal to 0. So now once we've combined all of our like terms, we're going to have x cubed plus 2x squared minus 13x plus 10 is equal to 0. So this is us putting our equation in standard form, multiplying it all out and having things in standard form. Now before we go on to part C of finding the degree, I want to make a few notes about standard form, and we're going to be doing that on the right side over here. So I'm going to zoom out just a little bit. So the generic version of standard form looks something like this, where A, B, and C, and so on are coefficients, or numbers out in front of the x. Then our n, n minus 1, n minus 2. This n is our highest exponents. So that's why we have like the 3 here, the 2 here, then a 1, and it keeps just going less and less until you get to this plus k at the end, which is your constant. So it's like this plus 10. Now I particularly want to talk about this term up in front. So this one right here. Now this ax to the power of n is the leading term, is what we're going to call that. Now, there may not always be a visible coefficient. So for instance, for problem number 1, we have x cubed. That's our leading term. Our degree comes from our leading term. That's going to be the exponent here. So in this case, n is the degree. And later on, in just a moment, we're going to look to see whether it's even or odd. But as we can see from our problem, well, our degree, our highest exponent, is right here at 3. So for part C, degree is 3. Done. The next question asks about the end behavior. And for that, we have to know about the degree, whether it's even or odd. We also have to know about the leading coefficient. In this case, the leading coefficient is the a value. We're going to be calling leading coefficient LC for short, just because it's so long. And we're going to be looking to see whether this leading coefficient is positive or negative. And that's going to help us determine the end behavior, or which direction the arrows are going to go. So I'm going to move this up just a little bit. So when we take a look at our different scenarios, we have 4 of them. I'm going to put them in a little box here. So like I said, we're going to look to see if the degree is even or odd. And we're going to look to see if the leading coefficient, which we're shortening to LC, is going to be positive or negative. So when I take a look at all these different scenarios, if I have an even degree and a positive leading coefficient, that might look something like this, right? That might just be an x squared function. And this shows me that both of the ends of my function are facing upward. Whereas if I had a negative leading coefficient and an even degree, it might look something like this, or a negative x squared with that reflection, which we learned about in our last unit. So this shows if we have an even degree with a negative leading coefficient, both ends are facing downward. Now for our odd degrees, that might be like what we have here, a cubic function. So those ends are going in opposite directions, and if we have a positive leading coefficient, it might look like this, or just a regular x cubed, where the right side is going up and the left side is going down. This is the direction the ends would be going. And then if we had our last box, an odd degree and a negative leading coefficient, that'd be like if we took an x cubed and reflected it. So it looks something like this, or negative x cubed. This is where the left arrow is up and the right arrow is down. So if we look at our particular circumstance, we don't even have to graph the whole thing to know where the ends are going to go. I can see right here that we have a 3 for our degree, which is odd, and a 1 out here. There's no negative sign, so this means it's positive. So we are odd and positive, which means that our end behavior, I'll write this down, our end behavior, oops, it's going to have our right side going up and our left side going down. And there you go. That's all you need. Last thing we have is to find our y-intercept. Now remember, y-intercept, I want you to write that as a point. Now for any y-intercept, our x value is going to be 0 because it's going to be on the y-axis. So you can kind of pretend, sorry, another email, you can kind of pretend as if you're plugging in 0 for all of the x's. Well, if you plug in 0 for all the x's, you're just going to go away and just be left with, oops, pardon me, the 10. Or another way you can think of this is this, if we go back to our notes, if we look at this plus k at the end, without any of our x's, whatever you have there, that is going to be your y-intercept. So again, factor, multiply everything together, take a look at that leading term to determine your degree and your end behavior, and look at that very last part for your y-intercept. Let's try this once more. I may have to do some scrolling because we're about to go over problem number 4, and our notes are going to be above it, so we may do some scrolling there. Let's take a look at problem number 4. When we take a look at problem number 4, I see that I need those roots of x is equal to -2, but what about that multiplicity of 2 right there, or that mult of 3? We're going to be spending some more time talking about multiplicities in our next video, but just a quick note on those. It's the number of times a root, quote unquote, happens, or how it interacts with the x-axis. We'll talk more about that, like I said, in our next video, but right now, all you need to know is that when you are setting this up, you're still going to find your factor like normal. So for a, we'll add 2 to both sides and get x plus 2, but now it's going to have a little exponent of 3, saying, hey, this root is happening 3 separate times. And this is going to be our function. So if here we wanted to find our standard form, we're going to take that x plus 2 cubed. Do not distribute the cube. That's the #1 most common algebra mistake ever. I'm going to write this out as x plus 2 times itself 3 times. And kind of do a longer FOIL like we did earlier. So I'll just do the first 2, first, outer, inner, last. We're going to get x squared plus 2x plus 2x plus 4 times x plus 2 is equal to 0. Once I combine my like terms, I get x squared plus 4x plus 4 times x plus 2. And then again, I want to make sure I multiply everything out. So we'll do x squared times x squared times 2, 4x times x, 4x times 2, and then 4 times x, and 4 times 2. So once I do that, I'm going to get x cubed plus 2x squared plus 4x squared plus 8x plus 4x plus 8 is equal to 0. Now, once I go through and combine all my like terms, we get x cubed plus 6x squared plus 12x plus 8 is equal to 0. So this is our standard form. Now remember, when we're looking at standard form and we want to determine our degree and our end behavior, we're going to be looking at our leading term, which is right here. Now, I'm going to take a look at my degree, or my highest exponent. So again, my highest exponent here is 3. It's just the degree 3 polynomial. For my end behavior, I see that we have 3, which is odd, and that we have a positive 1 out here. So, whoops. If I look at my little box up here, we have an odd degree, a positive leading coefficient. So my ends, I have the right side going up and the left side going down. Oops. So I'm just going to write that down for my end behavior. Right side's going up, left side's going down. And then for my y-intercept, remember you're going to write it as a point, so you're going to have your 0 first. And then we're just going to take a look at the very last number that we have without an x. In this case, it's going to be 8. So our y-intercept is 0, 8. So those are all the different features from an equation, but what about from a graph? Let's take a look at those. Those will go pretty quick. We'll just do 2 problems like that. So if we come here, each of these problems is going to have 4 questions of find the degree, find the number of turns, and we'll talk about that, determine if the polynomial is even or odd, determine the sign, positive or negative, of a leading coefficient. So it's kind of like doing the box that we just did, but backwards. We're going to be working on problems 1 and 3. We'll do 2 and 4 later on. So I'm going to leave some space over here for some notes for us. So first thing, number of turns. What does that mean? Well, our number of turns is, is any local maximum or minimum. So for instance, if we take a look at graph number 1 over here, there's a low point, but we end up going up. It's because we turned around. So we can say that's a turning point. Another place we have a turning point is if we come all the way up here and then turn around and move downward. That's a turning point. So if I was to list our number of turning points, I'll do B first. If we were to list our number of turning points, or number of turns, sorry, so many emails, there's 2. There's 2 turns overall. Now, the degree may be a little bit trickier. This kind of looks like a cubic function to me, and you would be correct to say that it's cubic, but a faster way that we can figure that out is that we can say that the degree is the number of turns plus 1. So since we found that there was 2 turning points in this graph, we can say that A, our degree, is 2, our number of turns, plus 1, so our degree is 3. There you have it. Now, for the last 2 questions, determine if the polynomial is even or odd, and whether the sign is, and determine the sign of the leading coefficient, we're going to be using our box for that. So if I'm going to really quickly redraw that box that was above. So again, we're looking at our leading coefficient, whether it's positive or negative, and then at our, there we go, our degree, whether it's even or odd, positive and even, both going up, even and negative, both going down, odd and positive, right is up, left is down. For negative odd, left is up, right is down. So I take a look at where this is and I see, okay, my left side's up, right side's down. That looks like this box right here, where we have an odd degree. So we've determined this is an odd polynomial. So this is odd. And we need to determine the sign. Well, this is a negative leading coefficient. So it's negative. And there you go. So let's try this with one more graph. If we take a look at problem number 3, first I'm going to do part B and look for the number of turns. Because anywhere we turn around, so from here we're going down and then up, and here we're going up and then down. So there's another point. And here we're going, oops, wrong button. There we go. Down and then up. So we have another one right here. So that means that our number of turns, we now have 3 turns. So if I look at the degree, I'm going to take my number of terms and add 1. So this is a degree 4 polynomial. Next, I'm going to ask myself, where does this land? Oops, sorry, that was supposed to erase. Why is this not erasing? Well, for some reason, that's on a laser pointer. There we go. So now I want to ask myself, where does this land in terms of the box? Well, I have both ends facing upward. There we go. So that looks like right here where we have an even degree and a positive leading coefficient. So my answers for C and D, C is even, and you could have maybe seen that from our part A. And then D was a positive leading coefficient. So again, I'm hoping all of this information is at least semi-review, that you've seen it before, even if you've forgotten it. Maybe you've learned the box before, maybe you haven't. We're going to spend more time practicing this in class, and we'll spend even more time talking about it tomorrow. Let me know if you have any questions, and I look forward to seeing you soon.